Okay, what's up, guys? I'm just getting everything set up here. Happy Friday. Um, okay. What is going on? All right. And there we are. All right. I think I also gave last week's lecture with the error that was causing everything to record in left channel only. Hopefully we have fixed that this week. I believe we have. That is my goal. So we're just finishing up section 2.2, and my hope is that this will be an actually a short class for Friday, because this section is nearly done, and I think we can make tie a nice bow on it pretty quickly and just give you back a few extra minutes of your day. Everyone loves that. So let's get right into it and see what we can do. I think we've got our usual two attendees already in the audience. Right on. What's up? Um, so let's get to it. Let's have a great time. So the gist of what we're gonna try to fully cover is Cauchy's theorem in comparison to this path independence theorem, and not really, or maybe not so much in comparison, but together with. That might be the right way to say it, to try to give a sense of what's going on in this complex domain with contour integrals, the existence of antiderivatives, and having a zero integral about closed curves, path independence, this kind of thing. So in section 2.1, we got this big theorem right at the end, the path independence theorem. And it says that if you've got a continuous function on an open connected set contained in the complex plane, remember, open connected sets are also called regions or domains, then the following are equivalent. Integrals are path independent, integrals around closed curves are zero, and there's a global antiderivative for f on this open connected set on this domain. Okay, last time what we got was something to kind of contrast with this. And the sort of vexing thing for us with all of this was the example where we started with this. So let's let gamma be the unit circle. We took the integral about gamma of 1 over z dz, and we got out 2 pi I. And we were like, oh, this seems kind of weird in some ways. Maybe it's not actually that bad. Mainly, we were like, crap. We've got this. This seems like this is wrong or something, right? We want to have a it feels like 1 over z should have an antiderivative, right? Because it should be the log, right? Logarithm. Well, the issue here is that we're not getting a global antiderivative on the open connected set, or on the appropriate open connected set. And the idea is that if you recall, let me grab this little picture from a bit ago. The domain of log z looked like, there we go. Actually, let me make this a little bit smaller if you don't mind. There we go. Gosh, it's so nice to be able to just resize things and copy paste them working on a tablet compared to a whiteboard. That is a big plus. So the idea is that if we are looking at like the unit circle, then we're looking at some, we're looking at like this, right? At like this, but like the domain of log z, we're getting, there's this gap right there, and 1 over z isn't even defined at the origin, right? And so we're running into these problems with things like 1 over z, where we're not breaking the theorem by any means. It's true that we got before, but we're a little bit confused about what this is telling us. It doesn't apply there, but what the heck is going on? So we moved into Cauchy's theorem in section 2.2, and what we started with is we got this very basic version of Cauchy's theorem in Theorem 2.2.1. And so in Theorem 2.2.1, we had an analytic function f with a derivative f prime that's continuous. On the inside, on and inside, a simple closed curve gamma. So on and inside a simple closed curve gamma. Then we got a 0 contour integral. So that idea is that if we have a nice simple closed curve, not self-intersecting or something, starts and ends, if f is continuous on and inside of that, then you're going to get out 0. Okay, fair enough. We kind of went back over to the this example sort of thing. We were like, all right, we got stuff with like log, right? We're going to end up dealing with, okay, this simple closed curve. We're either going to not have continuity inside of it, on and inside with like 1 over z, right? We're not continuous at 0. We're not defined at 0, right? And so, oh crap, okay, this is like on and inside, okay, that business. Then a little bit further on, we got into, and this is nearing the end of what we were doing last time, we were talking about simply connected regions. So recall that we went through these little examples. We have a simply connected region A, a non-simply connected region B, and then another non-simply connected region C. And the idea of being simply connected was that you could deform closed curves into points. When you have a you could deform closed curves into the simplest closed curve, which is a curve that starts and ends at the same point and never goes anywhere in between, right? Every closed curve starts and ends at the same point, but most of them tend to go somewhere else in between that. But the simplest closed curve is one where you start here and then you just stay there the whole time, right? Okay, fair enough. So you can think of it like that. If you can't deform a closed curve into a point, if it's not homotopic to a point, then the closed curve is kind of getting stuck on something inside the like missing in the space, whether it's a single point or if it's like a big hole or something. You can't deform it down to a point because you would have to pass through that region that's missing, right? It's kind of like a peg sticking out of the table and you can't pull the rubber band through it, if that makes sense. And so we got a version of Cauchy's theorem for simply connected regions. So if f is analytic on a simply connected region G and gamma is a closed curve in G, then the contour integral of f about gamma is 0. So notice we got rid of simplicity right here, right? We didn't require a simple closed curve, but we'll talk a lot more about the various conditions we can throw on closed curves, whether like rectifiability and other concepts like this in the next section. But the idea right here is mostly that we're looking at, as opposed to in this case with Theorem 2.1.9, we had an open connected set and f a continuous function. Okay. Now what we're moving to is an analytic function, which of course also has to be connected on a simply connected region G. Remember, a region is an open connected set, so a connected, simply connected open set G. One of the reasons why we like to say region, so you don't have to say connected, simply connected, region G, and a closed curve in G, right? So it's a slightly different context. And we got this another version of Cauchy's theorem. Okay. We went a little further and we basically we're continuing to recover or provide analogs of, via Cauchy's theorem, things from the path independence theorem in 2.1.9. So here we had f analytic on a simply connected region A. Then for any two closed curves joining 2 points in A, we had that the path, we were independent of the path. So we got independence of path for analytic functions on simply connected regions, as long as the paths remained in that region, right? That simply connected region A. Okay. And then this is this is the next result, and this is right after what we didn't quite get to this last time. It's the antiderivative theorem. It provides the third piece, the third analog to what we were looking at in 2.1.9, that first theorem that we keep recalling at the beginning of everything. Here we have f, an analytic function. Let me grab out my highlighter. F is defined in analytic on a simply connected region A, yet again. Then there's an analytic function big F defined on A that is unique, and that's a big deal, up to an additive constant such that f prime of z is equal to little f of z for all z in A. That's the antiderivative of f on A, or an antiderivative, right? Same kind of business as in usual calculus. Up to a constant, there you can get antiderivatives, and that's the business. There's a whole family of them, just shifted up or down, basically, or in the complex plane. The analog of that, and this just provides yet again analytic on a simply connected region analogs to. Sorry, why is my computer bugging on me right now? All right. I have like 1,000 tabs open, so it's probably my fault. So this just provided the analog to this third piece right here. So we went through and we said, hey, we started with the beginning of Cauchy's theorem with 2. This is the analog there. We're going to get 0 around closed curves. Then we got some path independence, and then finally we got antiderivatives. Okay, fair enough. Now let's kind of get back into this point we keep bringing up with the logarithm. So, what have I done? Have I pasted something over something else accidentally? Oh, there you go. Okay. There we go. Okay, nice enough. So, the existence of logarithms. Proposition 2.2.6, and this is what will answer our little question, our little concern about things like 1 over z as opposed to 1 over z squared contour integrated about the unit circle. And it also gives us a more robust version of what we were talking about with branches of the natural logarithm function. So if we have a simply connected region, the context that we're just always going to talk about in this chapter, or in this section at least, and we have 0 not in that simply connected region. Then there is an analytic function, big F of z, which is unique up to an additive multiple of 2 pi I, such that e to the f of z is equal to z. Okay, so we're going to prove this. We're going to go through the proof, but we're going to call this function f of z, we're going to write that's log z, right? Kind of the same as before. This is a branch of the logarithm, maybe a little bit more well explained than what we were saying previously with just choosing these, like what place the argument should be. This is a perfectly reasonable thing, but what we did before was perfectly reasonable, but this extends it to different domains. That is, instead of looking at just like the principal branch of the logarithm before, we may have weird sets, right? We may have things that look like this down here, this nightmarish looking spiral, this Tim Burton-esque, Nightmare Before Christmas looking area of the complex plane. What if we have this? What if we want to invert e to the z on this region? Are we just out of luck? No, we can do it. We can come up with something that does it. The big deal is that we don't have 0 in there, and we can come up with something that will take care of us. It's just going to be defined in terms of this unique function up to additive multiples of 2 pi, up to multiples of 2 pi I, right? The addition of multiples of 2 pi I, just like before with what we were doing with, choosing what the arg should be, right? Where you could keep adding 2 pi and stuff. This is the same business as before, except now we're just giving ourselves more flexibility in what domains we can choose, if that makes sense. So let's go through and prove this. And this just will give us a lot more. What we were talking about before is we were talking about branches of the logarithm on a specific domain. Just to be clear, I guess, in case this is at all seems strange. Oh, there we go. That's where I put it. Okay. Before we were saying like, hey, here's the domain of log z, right? And then we were coming up with a bunch of different branches, right? So I want to make this clear in case this seems at all confusing. When we were talking about branches of the logarithm before, we were doing branches of the logarithm on this domain, Now, what we're going to do is we're going to take this idea that we have, and we're going to expand it out so we can do branches of the logarithm on weird domains like this. Okay, that's what we're doing there. So there's branches of the logarithm. We've just been saying branches of the logarithm, but they're relative to the choice of domain is really the deal. Notice that what we were looking at before, that actually, let me even just put these two right next to each other. How about it? There we go. Okay. So here's two different domains for the logarithm. Notice neither of them contains 0, right? Neither of them. Neither of them have 0 in them. All right. And they're just two different places. They're just two different areas. They're both simply connected regions, right? If I grab a loop in here, there's nothing that's going to stop me from kind of shrinking that guy on down to a single point. If I grab a loop in here, even if it's like messy and it goes like around this thing, like I can't get stuck on anything because this goes all the way out forever, right? So I really can't, there's in some important kind of topological sense, these things are not different, right? Like they can sort of like be deformed into each other in some nice way that works well for the log function. So before when we were talking about branches, it was branches relative to this domain. Now we'll be able to talk about branches in exactly the same way, just relative to different domains. Okay, so let's go through and let's prove the existence of logarithms. So this all comes out of Cauchy's theorem. By the antiderivative theorem, that's our first step. There is an analytic function f with f prime of z equals 1 over z on A. Why is this? Well, because A doesn't contain 0, right? It's a simply connected region. F is if f is 1 over z, little f, then it's perfectly well defined and all that, right? It's all good. It's analytic. All right, analytic, well defined. Everything's good. So there is an antiderivative. Okay, easy enough. That just comes from the antiderivative theorem. Now, if we fix a point in z naught in A, then z naught is in the domain of some branch of the log function, defined as before, like we did in the beginning, right? Okay, cool. We're going to just use that. All right. Now, if we adjust f by adding a constant so that f of z naught is equal to the log of z naught, just like using the logarithm as before. So we can just add a little bit to f, right? Because f is unique up to addition of a constant. So we just add that difference in, right? And the constant there is pretty easy to see. It's f of z naught plus, or f of z naught, or log z naught minus f of z naught. Add that, and then you can get a whole new function f. So let's just assume we had f like to be that one in the first place. Then at z naught, you have e to the f of z naught equals z naught. Sorry, let me write that. The idea is that we can take, if f of z naught is not equal to log z naught. Sorry, I think I maybe said that out loud, and it probably was a little bit too many z naughts flying around. Notice that we could grab some different f. Let's call it like f tilde of z, defined to be f of z plus log z naught minus f of z naught. Right? This is just a constant right there, right? And so then when you do f tilde of z naught, you'll get f of z naught plus log z naught minus f of z naught, right? And these two guys cancel out, and hey, there you go, you've got one. And because this is just f of z plus a constant, it's still an antiderivative. So there's always an antiderivative that is equal to, that sends z naught to log z naught. All right. So that's what we're saying. And we might as well, since there always is one, we might as well just assume we took f to be that one in the first place, right? Okay. Then at z naught, e to the f of z naught is z naught, just by how the logarithm was set up to work. All right. Now we want to show that e to the f of z is z, and that's true for all z in A. We've only got it set up so it's true for one of them, right? Okay. The way we'll do this is we'll let g of z be equal to e to the f of z over z. All right. Well, because 0 is not in A, g is analytic on A, and since the derivative of f is 1 over z, right, since it's the logarithm, okay, then, bada boom, I mean, that's actually how we got f in the first place. We used the antiderivative theorem on 1 over z, right? Okay, then g prime, well, that'll be z times f prime of z, and you just pull the whole thing together, right? Z times the derivative of the top, e to the f of z, derivative of e to the f of z is derivative of inside, f prime of z times derivative of outside, which is e to the z, so e to the z with f of z plugged in, right? It's just chain rule. Okay, minus derivative of the bottom, which is derivative of z, that's 1, times the top, e to the f of z. Okay, that's cool. All over z squared. And notice, just multiply it out. What do we get? Z times 1 over z, well, that's just 1, right? So e to the f of z minus e to the f of z, it's going to be 0, right? 0 over z squared, which is just 0 on A. Hey, notice g is constant on A because it's got a 0 derivative on A. But g is 1 at z naught. So g is 1 on all of A, right? Why is g 1 at z naught? Well, because e to the f of z naught is z naught, right? So e to the f of z naught divided by z naught is 1. And hey, that's just g of z naught. So g is 1 at z naught, hence g is 1 on all of A. Therefore, e to the f of z is z, f of z is z, because if g of z is equal to 1, the constant function 1, then e to the f of z over z is equal to 1. So multiply both sides by z, and you're good to go. And you've got now the existence of a logarithm on all of A. Now the piece that we need to wrap up is the uniqueness piece. The uniqueness up to addition of multiples of 2 pi I. Now we'll let big F and G, big G be functions analytic on A, and we'll suppose that e to the big F of z is equal to z, and e to the g of z is equal to z. Let me zoom in a little on that, make sure this is big enough to see. E to the big G of z is equal to z. Then e to the f of z minus g of z is equal to 1, right? Just, take one divided by the other. All right. Also, e to the g of z minus f of z is equal to 1. So at some fixed z naught, f of z naught minus g of z naught is equal to 2 pi ni for some integer n, right? Why is this? Remember, it's because the exponential is periodic, yeah? So if you get the same value, then it must be at the same thing up to, we just differed maybe by a period, right? The input has to be the same up to the period. Okay. Just like if you have a sine of x equals sine of y, then x equals y plus, 2 pi n for some n, right? Because it's periodic. Okay. But all we have to do now is go, hey, derive both of them, and you get the same thing. So the derivative of the difference is 0 since it's just a constant, which, once again, from having a zero derivative meaning that you're a constant on the open connected region A, tells us that f minus g is equal to this constant on all of A, meaning they're the same up to the addition of that constant. And bada bing, we now have the existence of a unique complex logarithm on domains that look weird like this guy, as well as domains that look nice like that guy. How about that? That is kind of slick, right? And all we're really doing in this entire section, I think, is well summarized by this theorem. This is the kind of thing we want to be able to do. We want to be able to do all of the things we're used to doing, right? Like have inverses for the exponential function, right? Take e to the something, e to the ln and get out the identity, right? And we could do this on certain domains before, but on more complicated domains, on more complicated sets, it was not as apparent that we could. And the answer that we get from this is that we can. We always still can. We haven't lost an important property. That is, in the real variable case, if you look at the exponential map defined on whatever weird subset of the reals you want, you can still invert it and use the natural log. And it would sure be a shame if there were weird sets that you couldn't do that on in the complex plane. And as it turns out, it's not the case. It's not a shame, as long as you have a nice domain for the log function, something that satisfies the conditions of proposition 2.2.6, a simply connected region not containing 0. Then you have a logarithm that is unique up to multiples of 2 pi I. All right, not bad. So that concludes section 2.2, a little bit about Cauchy's theorem. Now in section 2.3, we're going to get a whole lot closer look at Cauchy's theorem and really delve into some of the details that we've kind of been brushing under the rug. But the meat of section 2.2, just to keep in your mind, is just the same as the meat of section 2.1, basically. We got path independence on open connected sets for continuous functions, and we got that this gave us some nice things. And then we went to looking at simply connected regions and analytic functions, and we re-derive the same things, and we'll get a whole lot more out of this. So let us, I think probably we can call this one early, unless anyone has some questions to throw in the chat. It's a relatively shorter section than the next one, which will be a bit more intense at certain points. The homework for this section is not too bad. It's just kind of computational, making sure that everyone feels good about actually doing some contour integrals. If you start to do one and you're like, wow, this is a lot more work than I want it to be, maybe ask yourself if there's some way to get around that using some facts like Cauchy's theorem. It's not hopefully too bad of an assignment, just a little bit of plug and chug for a few of them. at the start, but and then maybe one at the end. There's a little bit of recalling some good old techniques from earlier parts of the calc sequence. But other than just doing them for you, I don't think there's too many nice tricks to talk about. Yeah. Well, if this was an in-person class, I would ask if there are any questions, and I would wait until it got awkwardly silent, and then I would say, let's call it a day. But since I'm not seeing anything in the chat, and there's only one person here, let's just call it a day. Enjoy your Friday. Cool. See you next week.